we've all heard the quantum mechanics says everything has both wave and particle properties.
Yeah.
You know?
Wave-particle duality. It's fundamental.
Right. And for tiny things like electrons or photons, we actually see that. We see it in experiments.
Absolutely. It's well demonstrated.
But then, you look at a baseball or even just a single grain of sand.
Yeah.
Why don't they act like waves? Why aren't they diffracting around things or showing up in two places at once?
It definitely seems like a conflict with our everyday reality, doesn't it?
Totally. It feels a huge contradiction. So our goal today is really to dig into that apparent quantum classical divide.
Right.
We want to try and uncover how the internal sort of hidden quantum states of a big object actually dictate whether we can even see its external wave-like behavior.
That's a great way to put it.
And we'll be focusing on two really interesting concepts from the material you shared, phonons and the de Broglie wavelength.
Yes, exactly. And the de Broglie wavelength is a good starting point. The equation itself is simple. Lambda equals h over p Planck's constant divided by momentum.
Okay.
And technically it applies to everything, like you said. A baseball has a de Broglie wavelength.
But we don't see it. Why?
Well, it comes down to the p, the momentum. Momentum is mass times velocity.
Right.
And for anything macroscopic, even something moving incredibly slowly, the mass is just enormous compared to quantum scales.
So the p-value is huge.
Exactly. And since momentum is in the denominator, a huge momentum means a wavelength that's almost unimaginably small.
How small are we talking?
Often many, many orders of magnitude smaller than the diameter of a single atomic nucleus.
Wow, okay, so basically invisible, unobservable in any practical sense.
Under normal conditions, yes. That's why your baseball flies straight and doesn't, diffract around the bat in a noticeable way.
So it's there in theory, just ridiculously tiny.
Precisely. And the other piece of this puzzle, particularly for solid objects, is what's going on inside.
The internal state.
Yeah. Think about any solid. The atoms inside aren't just sitting there perfectly still, are they?
No, they're always vibrating, right? Because of temperature.
Exactly. They're jiggling around. But here's the quantum part. Those vibrations, that jiggling, isn't continuous. It comes in discrete packets of energy, quantized energy.
Ah, like photons are packets of light energy.
Precisely the same idea. These packets of vibrational energy have a name. We call them phonons.
Phonons, okay.
So you can think of a phonon as the smallest possible unit of vibration, or a quantum of vibration within that material's atomic lattice structure.
Like tiny packets of jiggle. I like that.
Yeah, packets of jiggle works. They're essentially the carriers of sound and, crucially, heat within many solids.
Okay, so we have this super tiny de Broglie wavelength for big objects, basically hidden from view. And we have these internal packets of jiggling energy, these phonons, related to heat. Is there a connection? I mean, does the internal jiggling, the phonon situation, actually affect whether we can ever hope to see that external quantum wave behavior?
It absolutely does. And this is really the core insight from the research.
Okay.
The possibility of observing an object's de Broglie wavelength, its coherence, its wave-like nature, it isn't separate from its internal state. It's fundamentally gated, you could say, by its phonon population.
Gated? How so?
Well, think about those phonons, especially the ones due to temperature thermal phonons. They represent random jiggling energy inside the object.
Okay.
This internal thermal noise, this bustling crowd of phonons, acts as a powerful source of what we call decoherence.
Decoherence, that's the process that destroys quantum states, right?
Right.
It makes them look classical.
Exactly. The internal phonon chaos effectively scrambles or blurs out the incredibly delicate phase information needed to see the wave-like properties of the object's overall motion, its center of mass.
So the internal heat, the jiggling, just washes out the external quantum weirdness. Fascinating.
It's a major barrier. But you mentioned earlier it's kind of a two-way street.
Right. What happens if we try to poke the bear? If we try to manipulate the object's overall motion, its center of mass, does that stir up the phonons?
It does. That's the other side of the coin. Back
Wow.
action. If you try to measure or control the center of mass, position, or momentum very precisely, trying to gently push it or see exactly where it is, that action inevitably kicks the internal state.
Kicks it.
It perturbs the phonon population. You can't isolate the external motion from the internal vibrations. They're fundamentally coupled. Measuring the outside affects the inside.
Okay, wow. So internal phonons cause decoherence, stopping us from seeing the wave. And trying to control or see the wave creates back action, stirring up more phonons.
That's the challenge. It sounds a bit like a catch-22, doesn't it?
It really does. So how do we break that cycle? Thankfully, the source material pointed towards a solution, this state-of-the-art experimental toolkit of cavity optomechanics. What's that about?
Cavity optomechanics. That's where things get really exciting from an experimental standpoint.
How does it help?
It basically gives us the incredibly sensitive tools we need to first understand this interplay between internal phonons and external motion, and then, crucially, to manipulate it.
Manipulate it how?
Primarily through cooling. Cavity optomechanics allows us to cool microscopic, but still large compared to atoms, mechanical systems down to unprecedentedly low temperatures.
Getting them close to their emotional ground state.
Exactly. The goal is to remove almost all the thermal energy, to quiet down those internal vibrations as much as quantum mechanics allows.
So basically chilling the object so intensely that the phonons just settle down. Freeze out.
That's the essence of it. You have to remember that thermal phonon gas, those random packets of jiggle, acts as this incredibly powerful intrinsic source of decoherence. It's built into the object because of temperature.
Right. It's always there, messing things up.
And it's the primary reason we don't see quantum effects in everyday objects. So the takeaway is profound. A macroscopic object simply cannot manifest its wave-like properties unless its internal vibrational state, its phonon state, is prepared in a state of exceptional quantum purity.
Meaning you have to get rid of almost all those thermal phonons. You need extreme quiet on the inside.
Extreme quantum quiet, yes.
And this is where cavity optomechanics comes in, providing the specific techniques to achieve that quiet. The research mentioned things like sideband cooling, feedback cooling.
Yes, and passive cooling, too. These are all sophisticated techniques that use light, often trapped in optical cavities, interacting with the mechanical object. They allow experimentalists to extract vibrational energy, phonon by phonon in some cases, cooling the mechanical resonator down towards its quantum ground state.
Removing the jiggle. Preparing it in that state of quantum purity you mentioned.
Precisely. And achieving that level of fine-tuning, that deep control over the internal phonon state, that's what unlocks the door.
Unlocks the door to what?
It unlocks the ability to actually prepare, manipulate, and observe the object's entire center of mass in deeply non-classical states.
States like superposition, being in two places at once.
Potentially, yes. We're not just passively observing anymore. We're effectively engineering its matter wave, sculpting it.
Wow. Engineering a matter wave. That sounds like science fiction.
It's cutting-edge physics, but it's becoming reality in labs.
So this isn't just academic curiosity then. What are the implications? Why should we care about sculpting matter waves?
Oh, the implications are huge. On a practical level, this kind of quantum control over mechanical objects is paving the way for sensors with sensitivities that are limited only by the fundamental laws of quantum mechanics itself.
Like what kind of sensors?
Think about detecting incredibly weak forces, maybe gravity at small scales, or measuring acceleration or mass with precision far beyond what's possible classically, pushing the absolute limits.
Okay, ultra-sensitive sensors. What else?
Well, beyond specific applications, it gives us a tangible, macroscopic platform to test the very foundations of physics. We can probe the transition between the quantum and classical worlds. Does quantum mechanics just stop working for big things, or is it always there, just hidden by decoherence? These experiments let us explore that boundary directly.
Testing reality itself, in a way.
In a very real way, yes. Probing questions about gravity and quantum mechanics, the nature of measurement, fundamental stuff.
So, thinking about all this, what's one big question, maybe a final thought, you hope this kind of research could eventually help us answer? Something for, the listener to chew on.
A final thought. Well, consider this. If we can truly engineer the internal quantum purity of an object, get rid of those phonons to the point where something you could, in principle, see could exist in a superposition, maybe in two places at once, what new possibilities does that open up? Not just for technology, but for our fundamental understanding of the fabric of reality itself. And maybe even what might it mean for the very definition of matter as we currently understand it?
That's a big question. Engineering matter waves to redefine matter itself. Lots to think about there.
Definitely. It pushes us to reconsider what solid and real truly mean at their core.